It's Tuesday, and that means Ted Keller, the science feller, he's here with another experiment.
Yes.
Yay!
Yay. And this time we decided we're doing some sound science.
Yes, a sound science. Nice.
Yeah, and I'll keep my day job.
Yeah.
Comedian. Yeah, that's right. Well, we had to go outside, and we did a little bit of experimenting. Well, we're taking science to the field, taking advantage of a sunny day, not necessarily a calm day, but it'll work. Shannon joining me today, and also Chris Smith doing his part for science, volunteering. There you go. We got some equipment here. I've got a measure that I use to determine at least 500 feet distance. Chris has the other end of a two-way radio, and of course, an air horn. So what are we doing, I wonder?
What do all these things have in common?
Yes, wonder. I think we're going to make a sound. We're going to do a little acoustic experiment and demonstrate how sound waves work, how fast they travel. So what we're going to do is we're going to stand here and we're going to send Chris yonder.
I like it already.
He's going to take a hike. He's dressed for it. He's going to run or walk or whatever he wants to do, and we'll check back with him in a minute as he gets to the other end of the field.
Speedy.
All right.
Speedy like a bunny.
Good luck. Yeah, he looks good for the part. Yeah,
Sure.
Yeah. We're trying to demonstrate the difference in the speed of sound versus something a little bit more instantaneous. Speed of sound actually does have a finite speed you can measure, but in order to do that, we have to have something that's instantaneous, and that's where the radio comes in.
Okay,
Yes.
so it's going to hit the radio before it travels to our ears.
If everything has gone according to plan, yes. This is more or less instantaneous, speed of light versus speed of sound. Because electromagnetic waves travel roughly at the speed of light, much, much faster. So we'll give Chris a shout out and see if we can hear a difference.
All right.
Ready? All right, here we go in science. Okay, Chris, here's the countdown. 7, 6, 5, 4.
3, 2, 1.
It worked. It worked. Now you're going to use the old echo, which we know is the delay based on that sound, and we've got a wall over there, and we're going to show that wall, and it's large enough. We tested it, and the whole idea here is we're going to attempt to use these blocks right here, custom cut by me.
Yeah,
there you
lovely.
go. And what we're going to do is snap them together real hard once. You heard the echo? Okay. What we want to do is practice a rhythm. So try doing it so it's like quarter notes. That, then that, then that, then that. So give it a try. Sounds about right? Yeah? Okay. Right. You must be musically inclined. Okay. On your mark, get set, go. Okay. Pretty good, 5.45, so only within a couple of tenths of a second, so that's pretty good.
Okay.
So then we'll figure out here in a minute how to convert that to the speed of sound. Well, we were joking, you handled the musical part and I handled the mathematical part.
That's right, that's right. It works great.
It worked out pretty well, but our calculations were interesting. Here's how we did this. The total distance to the wall was 170 feet, so total back and forth was 340, and then we had you do that 10 times, and the average was, it came out to about 5.45 seconds. So to figure out the speed of sound, we just took the distance total traveled by 1/10 of the time, and the answer we got was 623 feet per second, which is actually too slow. The accepted value is more like 1,100 feet per second. Now, this is perfect for anybody who does scientific experiments. The sensitivity there was the number of seconds it took to clap. And if we increased the wall distance, we probably could have gotten a more accurate reading. That's right.
Doesn't it also depend on the humidity, the particulate matters, things like that?
But ultimately, sound travels through the air by compressing the air, so it depends on density. And temperature is the biggest change that we have that affects the density.
All right, what about sound versus light?
Sound versus light. Yeah, light's traveling instantaneously at the speed of light, which is much, much faster than sound. And of course, we can use that in nature. Thunderstorms.
Right, absolutely.
That's right.
Yeah.
And if you ever wondered where this rule came from, maybe some of you know it, maybe some of you don't, we'll review it here. What you're basically doing is relying on the fact that when you see a lightning stroke, you see that more or less instantaneously. The sound is traveling about 1/5 of a mile per second. So what you do, 1001, 1002, maybe we've all done this, you get to 1005. In theory, that's 1 mile. So every time you go by increments of 5, the lightning stroke was probably about a mile away. It works pretty well. Again, you do have to make some adjustments for temperature and density, but and if it's too much lightning, you can't tell one flash from one boom.
Right.
But the scary ones are when you hear it, you see
know it.
boom, right at the same time.
Ted Keller, the science filler. Thanks for dropping by.